Tonight, we're going to break one of the simplest rules you think you know about the solar system. The rule that says all the planets calmly orbit and spin in the same direction, like gears in a giant, flat cosmic clock. Because here's what nobody tells you. One of those planets refuses to play along. One world the same size as Earth, in almost the same orbit, has decided to turn the wrong way, almost upside down, and at a pace that borders on the ridiculous. That planet is Venus. So let's start at the very beginning with a picture in your head. You know the one. All the planets circling the sun counterclockwise, seen from above the sun's north pole, each one spinning the same way it orbits. Mercury, Earth, Mars, Jupiter, Saturn. All broadly following the same rulebook laid down by the original rotating cloud of gas and dust. Now imagine you zoom in on Venus and press play. Instead of spinning counterclockwise like its neighbors, Venus turns clockwise. From that same vantage point, it is literally rotating backwards. If you tried to keep all the arrows in your mental diagram pointing the same way, Venus would be the one that forces you to grab an eraser. And it gets stranger when you put yourself on the surface. In theory, if you could somehow stand on those hellish rocks without being crushed by an atmosphere more than 90 times Earth's pressure, you'd watch the sun crawl up from the west and sink in the east. Very slowly, a single Venusian day, one full rotation, takes about 243 Earth days. Its year, one full orbit, is only about 225 days. On Venus, the day is longer than the year. Try to build a schedule around that. Your sunrise is months away. Noon is sometime next season. By the time tomorrow rolls around, your planet has already lapped the sun. So here's the paradox that should bother you. How does a planet so close to Earth in size, mass, and position end up with a spin that is backwards, almost completely flipped, and slowed to a crawl when the rest of the solar system mostly behaves itself? What twisted the rules for this one world and left the others mostly intact? Because here's what nobody tells you when they show you that neat, flat diagram. Beneath the apparent order, there is violence, there is chaos. There are long-forgotten collisions and subtle tugs of gravity encoded in every tilt and every rotation. Venus is not just a boring, cloudy twin of Earth. It is a crime scene. Its slow, retrograde spin is the key piece of forensic evidence, pointing to ancient impacts, tidal forces, and atmospheric torques that we're only beginning to reconstruct. Now, let's begin to read that evidence. So let's pin down what makes this crime scene so bizarre. Almost everything in the solar system spins one way. Venus spins the other. And it does it in slow motion, like a planet trying to press pause. If you could stand on those hellish clouds and somehow not melt, you would watch the sun crawl up from the west and sink in the east over the course of months. One Venus day is about 243 Earth days, longer than its 225-day year. That's not just quirky. That is a full-blown paradox baked into the clockwork of the inner solar system. Because here's what nobody tells you. There is a basic rule hiding underneath all those textbook diagrams. So, let's start at the very beginning. Our solar system formed from a collapsing cloud of gas and dust, a huge rotating fog that flattened into a disk under its own gravity. The planets were born inside that disk, growing from the same swirling material, so they inherited its general direction of spin and orbit. You know the one, that flat picture with all the planets circling in the same direction, like cars on a racetrack. Viewed from above the sun's north pole, almost every major planet spins counterclockwise and orbits counterclockwise. That's the pattern. That's the rule. Venus, from that same vantage point, it rotates clockwise. with its axis tilted about 177 degrees, as if someone grabbed the planet and flipped it almost completely upside down. On paper, that shouldn't happen. Not to an Earth-sized world sitting right next door. If we can't explain why Venus broke the rule, then we don't really know how hard it is to break a planetary system in the first place. Are our orbits and rotations robust, locked in for billions of years? Or are they fragile, one bad collision away from a slow, backward spin and a runaway greenhouse? This is where the emotional stakes sneak in. Because once you admit that Venus's rotation is a genuine mystery, you're forced to ask some uncomfortable questions. Did something catastrophic happen there that could, in principle, have happened here? Could Earth have taken a different path and ended up with the sun rising in the west over a toxic ocean of lava clouds? And if Venus can be twisted this far, what about Earth-like exoplanets we're finding around other stars? When we say habitable, we usually picture a calm blue marble, but a planet with a year shorter than its day, spinning backwards under a crushing atmosphere, might look deceptively Earth-like from light years away. Now let's begin to pit the suspects against each other. In the next part, we're going to weigh two competing explanations. Ancient cosmic violence, where a giant impact mangles Venus's spin, versus slow, relentless torques from sunlight and tides that gradually flip it over. The surprising part, the evidence doesn't neatly pick a side, and that tension is exactly where the real story lives. So before we throw Venus into the cosmic boxing ring and watch those theories fight it out, can we make a tiny deal with you? If the idea of a planet spinning backwards, with a day longer than its year, even nudges your brain a little, that's your sign to tap like and hit subscribe. Because here's what nobody tells you. Those 2 clicks from you are almost effortless. But for this channel, they're like adding extra gravity to our little corner of space. They pull in more curious minds. They tell the algorithm this mystery is worth orbiting around. And they let us tackle even stranger questions. Questions like, why is Uranus practically lying on its side? How did Mercury end up in that bizarre spin-orbit lock where it rotates 3 times for every 2 trips around the sun? You know the one. The flat solar system picture, where everything feels simple and clockwork and polite. Venus is our reminder that the universe does not care about polite. And if you want more episodes where we peel back that flat picture and look at what's really going on with these misbehaving worlds, that support genuinely makes it possible. So here's how you can join the investigation right now. Drop a comment and tell us which explanation you're currently rooting for. Are you on team ancient cosmic violence, where a Mars-sized impactor slams into early Venus and sends its spin tumbling? Or are you betting on the slow, relentless twist? Tidal forces from the sun and that crushing atmosphere gradually breaking and flipping the rotation over billions of years? Or do you suspect something even weirder hiding in the data that we haven't talked about yet? We're going to come back to those theories. We're going to test them against actual measurements from orbiters and radar maps and from upcoming missions like Veritas, Envision, and Da Vinci that will read Venus's crust and atmosphere like a crime scene report. When we finally weigh the evidence, you'll be able to see whether your hunch holds up or whether Venus pulls one more reversal on you. And just to be clear, this isn't going to be a quick list of fun facts about how hot Venus is. This is a deep, cinematic journey through its past. We're going to rewind the solar system, reconstruct the spinning cloud that became the planetary disk, and watch how a world that once looked like Earth's twin ended up with the sun rising in the west. Because once you understand that, you won't just picture Venus differently. You'll picture the entire solar system differently. So, let's start at the very beginning. Now that we've raised the question and the stakes, we need a clean baseline. What does normal planetary spin even look like before Venus breaks the rules? So let's start at the very beginning. Before we can talk about a planet spinning the wrong way, we need to walk back into that classroom where you first met the solar system. You know the one. The poster with the bright yellow sun in the center, a perfectly round fireball, and then those neat colored circles marching outward across a dark, flat background. Everything arranged on a single flat line, everything moving in the same direction, like a giant cosmic clock laid down on a table. In that picture, Mercury hugs the sun first, then Venus, then Earth, then Mars. After the little asteroid belt divider, you get the heavyweights: Jupiter, Saturn, Uranus, and Neptune. 8 planets, one central star, all tracing out tidy orbits in one flat plane. From above the sun's north pole, they all glide counterclockwise. Same direction, same sense of motion. Because here's what nobody tells you when you first see that diagram. It's not just the orbits that line up. The spins mostly line up too. If you hover above the sun's north pole and look down, Mercury rotates prograde. Venus is the exception we're heading toward. Earth spins prograde, giving you the familiar west to east motion of the sun across your sky. Mars spins prograde. Jupiter, Saturn, and Neptune all rotate prograde as well, rolling along like wheels turning the same way on the same highway. Imagine putting 8 coins or marbles on a glass table. You give them all a push so they slide around in circles in the same direction. And while they slide, you spin each one the same way with your finger. That's the textbook solar system. Flat table, single plane. Same direction for the orbits. Same direction for almost all the spins. There are quirks, of course, and your teacher might have mentioned them like fun facts. Uranus is tipped over on its side by about 98 degrees. So in that flat picture, it looks like it's rolling rather than spinning. Pluto, back when it was on the classroom wall, had an orbit tilted about 17 degrees to the main plane, cutting above and below that flat reference. Oddballs, yes. But still more like tilted wheels than wheels suddenly reversing and driving against traffic. So the mental model you've carried is simple. A flat solar system. One main plane. Everything going the same direction. That repetition is not an accident. Flat. Same direction. Flat. Same direction. And yet something is above the planets. Something is below them. One world refuses to play along with the clockwork. In the next part, we're going to take that tidy, flat picture you grew up with and let Venus punch a hole straight through it. So let's actually look at that picture Venus just punched a hole in. You know the one. The neat side view of the solar system. All 8 planets lined up in a perfect flat row. Little circular orbits like train tracks. The sun in the middle, like a polite traffic light. It's clean. It's satisfying. And it quietly lies to you. Not because it's wrong in the way a conspiracy video is wrong, but because it's incomplete in a very specific way. It trains your brain. It tells you over and over that space is orderly, that there's one main plane, that everything agrees on what around the sun should look like. Because here's what nobody tells you. The more you see that flat diagram, the more you start to believe that's what reality feels like. Your mind does something sneaky with repetition. After a few textbooks, a few documentaries, a few posters on classroom walls, you start to assume that if you climbed into a spaceship and flew straight up, out of that plane. You just leave the solar system behind. One clean escape vector. Below you, a thin disk of orbits. Above you, empty nothing. No planets. No drama. Just blank space. That's the first hidden assumption baked into the picture. That there's a real, physical up and down for the solar system, and once you leave the orbital plane, the story is over. And yet something is above the planets. Something is below them. Asteroids on tilted paths. Dwarf planets on wild inclinations. Long-period comets fallen in from angle the diagram never even hints at. The picture never told you they existed, so your intuition quietly erases them. The second hidden assumption is even sneakier. Those diagrams almost never bother to show you how the planets themselves are spinning. You get arrows for orbits, maybe a label for tilt, but not a clear sense of rotation direction. So your brain does the lazy, perfectly human thing. It copies and pastes. If Earth spins one way, then surely Mars, Jupiter, Venus, all play by the same rotational rulebook they started with, right? On the page, nothing contradicts that. The planets are drawn as identical circles, scaled down marbles, all politely aligned. No one planet is shown upside down. None are drawn with a big, bold arrow screaming, actually going the other way. So why would you ever suspect that one world's day is literally backwards? This is why Venus hits so hard. The moment you learn that one planet doesn't just tilt a little, but effectively spins upside down and backwards, the tidy mental model starts to crack. If that flat, calm diagram hid something this dramatic, what else is it hiding? What's really happening above and below that plane? Now let's begin to follow that crack. Because once Venus breaks the illusion, the whole idea of a simple, flat solar system doesn't just bend. It starts to fall apart in 3 dimensions. So let's lean into that crack and do something you never see in the textbook picture. We're going to climb, not along the flat disk, straight up, away from it. Imagine you're in a small ship, hovering just above Venus's unbroken ceiling of clouds. The planet is slowly rolling the wrong way beneath you, the sun creeping across its sky in reverse. You point the nose of the ship at what we'll call up, to a line perfectly perpendicular to the orbital plane, and fire the engines. If that childhood diagram were the whole truth, what would you expect to happen next? In a few hours, Venus would be a shrinking marble below you. The ring of planets would fall into a thin, glowing line. And then, nothing. Just empty space above and below, with the solar system as a flat plate hanging in the dark and distant stars in every direction. Because here's what nobody tells you. That clean, flat picture is lying by omission. As you keep accelerating away from Venus, you don't leave the solar system behind. You rise into its thickness. First, you pass the slightly tilted paths of the other planets, each orbit tipped a few degrees off the ecliptic. Mercury's track slices a little higher, a little lower, like a razor-thin rail. Mars and Earth form a subtle, warped sheet around the Sun. You know the one, the diagram where the orbits look like perfect circles on graph paper. From your cockpit, it already looks more like a nest of rings with depth. Climb higher, and the picture gets messier. You cut through the main asteroid belt, where families of rocks loop 10, 20, 30 degrees above and below the plane. Some swing so far out of line that above and below start to feel like bad habits rather than directions. Then farther still, you cross the Kuiper belt and the scattered icy worlds beyond Neptune. Their orbits twisted, stretched, even flipped. And yet, something is above the planets. Something is below them. Keep going, and the neat disk dissolves into a vast, roughly spherical cloud of comets. The Oort cloud. Trillions of icy bodies in orbits pointing every which way, forming a three-dimensional halo that makes the planetary plane look as thin as a sheet of paper inside a fog. So if orbits can tilt, twist, and scatter like that, what about spins? Is Venus's backwards rotation really an exception, or just another way gravity scrambled direction in 3 dimensions over billions of years? To answer that, we can't just hover over Venus. We have to rewind everything, strip away the planets, unspool their orbits, and watch the solar system collapse and spin itself into existence from a raw cloud of gas and dust. What happened in that first chaotic million years that could flip a world and make it turn the wrong way? Now let's begin to find out. So before we dive into that collapsing cloud and start flinging protoplanets around, we should be honest about what we're really trying to fix here. You don't just want a trivia answer like Venus spins backwards. You want to know why. You want to know what broke in that clean, flat classroom diagram you grew up with. You know the one. All the planets as neat circles, all the arrows curving the same direction, all the spin axes politely tilted just a little. In that picture, rotation feels like a simple rule. Planets form in a disk, they orbit in that plane, they spin the same way the disk spins. Done. Because here's what nobody tells you. That rule is only step 1, and Venus is what happens when you zoom out to step 2, 3, and 4 over billions of years. So our agenda in this video is really a 3-part repair job on that mental model. First, we're going to lay out how planets are supposed to spin according to formation theory, how a collapsing cloud of gas and dust sets the direction of the disk, how that disk sets the direction of orbits, and how that, in turn, sets the default spin for baby worlds. Then we'll ask the uncomfortable question. If that's the rule, why is Venus rotating the wrong way, with a day that's longer than its year, and a sun that crawls up in the west and sinks in the east? Second, we're going to walk through the 2 big categories of suspects. On one side, the violent options, giant impacts that can slam a young planet, tilt it, slow it, maybe even flip it nearly upside down, like we think happened to Uranus. On the other side, the quiet but relentless options, tidal breaking from the sun's gravity and torques from Venus's insanely thick atmosphere, gradually twisting its spin over hundreds of millions of years. Which matters more? And do they actually work together instead of competing? Third, we'll ask what this all means beyond Venus. If an Earth-sized planet in our own solar system can end up with a 177-degree tilt and a retrograde rotation, what does that say about Earth's past? And about the normal exoplanets we keep finding in tight, weird orbits around other stars? Are we the rule, or the exception that just looks normal in a flat diagram? Because once you see how fragile that tidy disk picture really is, you start to replace it with something else. A dynamic, 3-dimensional evolving structure where spin axes wander, orbits trade energy, and rotations can slow, stall, and even reverse. So let's start at the very beginning of that process in the next section and watch those rules get written. And yet, something is above the planets. Something is below them. Out there, around other stars, we're already seeing worlds with tilts and spins that make Venus look almost modest. Venus might not be a lone freak. It might be our local preview of just how strange normal rotation really is. Now let's begin. So if Venus isn't a lone freak, what exactly is wrong with it? To really see how twisted this planet is, You need to break its rotation into 3 separate mysteries, because here's what nobody tells you. Venus spins backwards is actually 3 different crimes at the same cosmic crime scene. There's the direction of the spin, there's the speed, and there's the tilt. Each one is weird on its own. Together, they turn Venus into a full-blown forensic file. First, direction. Most planets in the solar system rotate the same way they orbit the sun, spinning counterclockwise if you look down from above the solar system's north pole. Venus doesn't. It rotates retrograde, clockwise. So if you could stand on that hellish surface, the sun would crawl up in the west and sink in the east. That's not a tiny quirk. That's a sign that something has grabbed the planet by the equator and twisted hard. Second, speed. Venus takes about 243 Earth days to complete one spin. That's longer than its year, which is only about 225 days. A Venusian day is so slow that the planet almost forgets it's supposed to be rotating at all. Earth, Mars, even tiny fast-spinning bodies like Jupiter all got their spin from the same collapsing cloud of material. So what slammed the brakes on Venus? Was it the sun's tides, its monstrous atmosphere, or both working together over billions of years? Third, tilt. On paper, Venus's axial tilt is about 177 degrees. In plain language, it's basically upside down. Earth's 23.5 degree tilt gives you seasons. Venus' near 180 degree tilt means its north pole is effectively where you'd expect its south pole to be. That tilt could come from a giant impact, from long-term gravitational torques, or from a messy sequence of smaller hits and tidal nudges that flipped the planet more than once. Here's the key move. Those 3 mysteries don't have to share a single cause. An early collision could have knocked Venus off balance and set its tilt. Slow, relentless tidal forces from the sun could have bled away its spin speed. Its dense, super-thick atmosphere could have acted like a giant hand on a flywheel, trading angular momentum between air and rock until the rotation reversed. So, let's start at the very beginning of Venus's story and treat each clue separately. Because once you do that, a deeper question appears. Did Venus begin as an Earth-like world that got progressively twisted? Or was it always on a path to be strange? If Earth's twin can end up rotating backwards, upside down and barely moving, how secure is our own axis, our day length, our climate history? You know the one, the stable, friendly Earth picture that lulls you to sleep. And Venus isn't alone. Uranus is tipped over on its side. Mercury is caught in a spin-orbit dance with the sun. In the next section, we're going to meet these rotational oddballs and see how their stories might help decode what really happened to Venus. So if the solar system is full of rotational oddballs, how did any planet end up spinning the right way to begin with? To answer that, we have to rewind. Hard. Now let's begin by doing something dramatic. We roll the clock back 4.6 billion years, until Venus, Earth, Uranus, all of it, simply vanish from the picture. No sun, no planets, just a cold, dark region of space that doesn't look like much at all. So, let's start at the very beginning. Before there was a solar system, there was a molecular cloud. You can picture it as a gigantic, ghostly fog of gas and dust stretching for light years, so thin that you could fly through it and never feel a thing, and yet massive enough that gravity still has plans for it. A molecular cloud is mostly hydrogen and helium, the simplest elements in the universe. But laced through that fog are heavier elements: carbon, oxygen, silicon, iron, built in earlier generations of stars and blown out by supernovae. Because here's what nobody tells you. Every rocky world you've ever heard of is made from the ashes of dead stars, Venus included. For a long time, this cloud just drifts, quiet, almost perfectly balanced. Then something breaks the calm. It could be the shockwave from a nearby supernova, or the tidal nudge as the cloud passes a spiral arm of the Milky Way. Whatever the trigger, one region of the cloud starts to collapse in on itself under its own gravity. As that region shrinks, it doesn't fall straight inward. It can't. There's always some tiny leftover swirl of motion, some slight imbalance in how the gas is moving. And gravity does something sneaky with that. The smaller the collapsing region becomes, the faster it spins. Like an ice skater pulling in their arms, the rotation speeds up as the radius shrinks. That tiny initial spin, almost an afterthought, suddenly matters a lot. It gives the entire forming solar system a preferred direction, a built-in this way around for future orbits and rotations. Is it perfect? Not at all. But it's enough that, by default, everything is supposed to turn the same way. As the collapse continues, the spinning cloud can't just keep getting smaller in all directions. The vertical motion gets squeezed out. The rotation wins. The whole thing flattens into a disk, a wide, rotating plane of gas and dust with a growing baby star, our sun, blazing to life in the center. Inside that disk, rings of material begin to clump together. Pebbles become boulders. Boulders become embryos of planets, orbiting in roughly the same flat plane, all inheriting that original direction of spin. This is where Venus is supposed to be, just another well-behaved child of the disk. So what went wrong? In the next section, we're going to zoom into that newborn disk and watch the chaos that can twist a normal spin into something utterly backwards. So if Venus is the rebel, we need to understand what all the well-behaved planets were supposed to do. Under normal circumstances, the universe is boringly consistent here. It loves to copy-paste. So let's start at the very beginning. Picture that original cold cloud of gas and dust, light years across, drifting in interstellar space. Gravity starts to pull it inward. As it collapses, any tiny initial spin it has can't just disappear. Because here's what nobody tells you. In space, spin is like a budget. You can move it around, but you don't get to erase it. As the cloud shrinks, it spins faster, just like an ice skater pulling in their arms. Wide spin becomes tight spin. Slow becomes fast. That's conservation of angular momentum in action, and it turns a lazy, tumbling cloud into a whirling system. You can almost feel the tempo picking up as everything falls inward. But a spinning cloud doesn't stay a cloud for long. The faster it turns, the more it flattens. Material trying to fall straight and gets redirected into orbit around the growing protosun, forming a thin, rotating disk we call the solar nebula. Now most of the mass is circling in the same direction, in almost the same plane, like cars on a cosmic racetrack instead of a random, three-dimensional swarm. Inside that disk, things get busy. Tiny grains collide, stick, grow. Pebbles become boulders. Boulders become planetesimals, and those merge into protoplanets. Crucially, they're not just orbiting the protosun in that shared plane. They're also spinning the same general way the disk spins. Why? Because every collision, every merger, passes along a little bit of that original disk rotation. Here's one way to picture it. Imagine a record player spinning on a table. You know the one. The flat black disc turning smoothly in one direction. Now you sprinkle coins onto it. At first they rattle and wobble, but as friction grabs them, they start to slide and drift, and almost all of them end up moving around in the same direction as the record. Not perfectly, not identically, but with a clear preferred motion. The early solar system works the same way. The record is the spinning nebula. The coins are clumps of rock and ice, and yet something is above the planets. Something is below them. Tiny deviations in tilt, a few degrees off the main plane, but almost never a complete reversal. So under this simple, elegant picture, Venus should be just like Earth, orbiting prograde, spinning prograde, aligned with the disk that built it. The fact that it's not, that it's essentially upside down and rotating backwards, is a giant red flag. It tells you that the calm disk story is not the whole story. Something dramatic grabbed that neat rotation budget and rewrote it. In the next section we'll ask, what kind of cosmic violence does it take to turn a normal spin inside out? So if Venus's spin has been rewritten, who's holding the pen? To answer that, we have to zoom out and rewind the whole solar system. Because here's what nobody tells you. Planets are the survivors of a bar fight. So, let's start at the very beginning. Forget the calm, flat diagram with neat, circular orbits. Picture the young solar system as a thick, churning cloud of rock and ice fragments, from dust grains to mountain-sized boulders to whole baby worlds. Thousands of planetary embryos were sharing overlapping paths. They didn't politely pass each other. They slammed together. When two of these bodies met, there were only a few options. They merged into something bigger. They shattered into fragments. Or they grazed each other, flinging debris across space and twisting their spins like a brutal cosmic wrench. This wasn't a rare exception. This was the main way the inner planets grew. And yet, something is above the planets. Something is below them. Not in the sense of up and down, but in terms of energy. Every collision could kick a world into a slightly different orbit, or leave it rotating faster, slower, or tilted at some wild angle compared to the original disk plane. A single badly aimed hit could turn a steady, prograde spinner into a lopsided, wobbling mess. We know this isn't just theory because we have a crime scene in our own backyard. You know the one. The leading idea for how the moon formed is that a Mars-sized body, Theia, slammed into the early Earth. That impact would have melted huge parts of both worlds, sprayed a ring of debris into orbit that later clumped into the moon, and radically reset Earth's rotation and tilt. If our planet went through something that violent, what were the odds Venus walked away untouched? Simulations of young planetary systems show just how chaotic this phase is. Run the same starting conditions 100 times, and you don't get 100 identical Earths and Venuses. You get a wild spectrum. Some planets spinning once every few hours, some dragging through a rotation that takes months, some tipped over like Uranus, some even pushed into retrograde. The sequence, angle, and timing of just a handful of major impacts can completely rewrite a planet's spin story. So here's the uncomfortable question. Did Venus draw the short straw? Did it take one especially unlucky glancing blow that nearly flipped it, then another that finished the job, leaving it essentially upside down and easy for gravity and tides to nudge into a slow backward rotation? In the next section, we'll see how those early hits, combined with billions of years of subtle forces, could lock in the strangest day in the solar system. So if Venus drew the short straw, here's the part that really stings. On paper, it was supposed to be our twin. Same neighborhood in the solar system. Almost the same distance from the sun. Similar size, similar mass. Likely carved from the same collapsing cloud of rock and metal. From far away, you'd look at those two worlds and say, you know the one. that one could be another Earth. And you'd be right to think that. At least at the beginning. Because here's what nobody tells you. In most early formation models, Venus and Earth don't start out as opposites. They both condense inside that flat proto-planetary plane. Both inherit a normal, prograde spin from the swirling disk. Both end up with modest tilts. Not this wild 177-degree, nearly upside-down situation. Some simulations even suggest that, for a while, their surface conditions might not have been that different. Liquid water, thinner atmospheres, not ruled out. Picture two newborn planets, spinning the same way, orbiting the same star, with day lengths that aren't completely absurd. Gravity is sculpting continents. Volcanoes are outgassing. Early atmospheres are thickening, but nothing yet screams one of these will become a slow-turning pressure cooker. If you could pause the solar system right there, would you honestly be able to tell which one would end up with oceans and which one would end up with oceans of lava-hot rock? Fast forward a few billion years. The paths have split so hard they barely feel related. Earth keeps a brisk prograde rotation, a comfortable 24-hour day, a tilt that gives you seasons instead of total chaos. Venus, its atmosphere crushes at more than 90 times Earth's surface pressure. The temperature soars to around 460 degrees Celsius, hot enough to melt lead, day or night, pole or equator. And its rotation has crawled to a halt and then gone backward, taking 243 Earth days to complete a single retrograde spin, while it whips around the sun in just 225. What happened in between? What did space throw at one twin that it didn't throw at the other? Because once you see Venus and Earth as near duplicates at birth, their divergence stops being just trivia and becomes a natural experiment. Same starting conditions, slightly different histories, radically different outcomes. Venus's bizarre spin, frozen in that slow backward orbit, is like a fossil record pressed into the planet's interior and atmosphere, encoding every shove, tug, and tilt it ever experienced. If we can decode that record, we don't just explain one weird planet. We learn how fragile Earth-like really is. Now let's begin to interrogate the prime suspects. Scientists have narrowed Venus's backward spin to two main culprits: cataclysmic impacts and relentless tidal torques. And the twist is, neither one quite fits the picture on its own. So let's start at the very beginning of the crime scene. If you want a planet to spin backwards, the most dramatic way to do it is to hit it hard. The first suspect in Venus's case file is a giant impact so violent it could have knocked the whole world onto its head. Here's the basic picture. Early in the solar systems, planets weren't polite, finished worlds on neat, flat orbits. They were growing, crashing, merging inside a swirling cloud of rock and ice, all under chaotic gravity. In that chaos, an Earth-sized proto-Venus could have been sideswiped by a Mars-sized body at just the wrong angle. Not a dead center smash, but an oblique, glancing blow that twists more than it shatters. You know the one. It's the same class of event we invoke to explain how Earth got its moon, and how Uranus ended up tilted more than 90 degrees, rolling around the sun on its side. Because here's what nobody tells you. Giant impacts are not rare exceptions in planet formation. They are the rule that carves the final shape and spin of worlds. In computer simulations, you can watch this play out. Take a young Venus, similar in size to Earth, spinning in the same direction as most planets. Now slam it with a Mars mass projectile that cuts across its equator at an angle. The impact injects a huge amount of angular momentum, but not neatly aligned with the original spin. The result? The axis can tip past 90 degrees, even all the way to something like Venus's current 177-degree tilt, so the planet is effectively upside down. From above the sun's north pole, it now appears to rotate clockwise instead of counterclockwise. But the collision doesn't just twist the spin. It excavates mantle, melts crust, and can blow off or rearrange the early atmosphere. A shock like that could have stripped lighter gases, reshuffled volatiles, and left Venus with a thick, altered envelope that later evolved into the crushing, runaway greenhouse atmosphere we see today. In that sense, the impact isn't just a spin doctor, it's a climate architect. And yet, something is above the planets. Something is below them. In the same way, above the tidy textbook picture of quiet orbits, there's a hidden layer of violence sculpting everything you see. If Earth can grow a moon from a colossal impact, and Uranus can be toppled over, why wouldn't Venus also carry the scars of one spectacular hit? There's a catch, though, and it's a big one. These simulations are great at flipping axes, but they tend to leave planets spinning relatively fast. Venus today rotates so slowly that its day is longer than its year. A single turn takes about 243 Earth days. How do you go from a post-impact spin to that glacial crawl? That's where our second suspect enters the picture. The quiet, relentless pull of tides and atmosphere, working over billions of years to finish what the impact started. So let's talk about a force that doesn't arrive with a crash. It arrives with a whisper. The sun's slow, relentless grip. You've seen tides on Earth, right? Oceans rising and falling as the moon and the sun pull on them. Now scale that idea up to an entire planet. Tidal forces are what you get when gravity pulls a little harder on one side of a world than the other. The side of Venus facing the sun feels a slightly stronger tug than the far side, and that tiny difference stretches the planet, raising subtle bulges in its rocky body and in its atmosphere. Here's the twist. Those bulges don't sit neatly between Venus and the sun like a straight line in a flat diagram. Because Venus is rotating, the bulges get dragged a bit ahead or a bit behind the line, connecting the two. And once that happens, gravity has leverage. The sun can grab those offset bulges and twist, exerting a torque that tries to realign them. That torque can act like a cosmic brake, or, in some configurations, a very slow accelerator. Because here's what nobody tells you. You don't need a giant impact every time you want to change a planet's spin. You just need time and tides. If the bulge leads the sun, the torque tends to slow the rotation. If it lags, it can speed it up. On Earth, oceans and a thinner atmosphere limit how far this can go. On Venus, the game is completely different. Venus's atmosphere is a monster. Surface pressure, more than 90 times Earth's. Thick carbon dioxide loaded with clouds of sulfuric acid. And high-altitude winds that whip around the planet in just about 4 Earth days. That super-rotating atmosphere responds strongly to solar heating, creating powerful atmospheric tides. Waves of pressure and motion that march around the planet as its day side bakes and its night side cools. Those tides shift mass in the air, which means they shift where gravity can grab. Now, let's begin with a mental picture. Imagine an early Venus spinning prograde, faster than it does today, maybe with a day lasting only a few Earth days. Solar tides in the solid rock and in that dense, turbulent atmosphere keep raising bulges that are just slightly out of line with the sun. Every Venus day, every Venus year, the sun pulls on those bulges and robs a tiny bit of rotational energy. It's glacially slow, but it never stops. Over hundreds of millions, even billions of years, models show that this tidal braking can drag a once fast, Earth-like spin down toward a standstill. And when a planet's rotation becomes that sluggish, something strange happens. Small asymmetries, including atmospheric tides, can tip the balance and let the spin slip through zero into retrograde. From our reference plane, the whole world seems to have decided to turn the wrong way. So was Venus simply battered once and left alone? Or has the sun been quietly twisting it ever since? Hold that question, because our third suspect will push this tidal story into even weirder territory. That third suspect turns out not to be a single event at all, but a partnership. Violence and patience working together over billions of years. Because here's what nobody tells you. Most modern models don't pick a lone culprit for Venus's weird spin. They tell a story in chapters. So, let's start at the very beginning. In the standard picture, Venus forms inside that same rotating cloud and flat, protoplanetary disk as Earth. It should come out spinning prograde, turning the same way it orbits, with a day measured in hours, not centuries. You know the one. A young, molten world, hammered by impacts, but broadly behaving like a normal planet. Then the script gets rewritten. Imagine an early Venus taking a glancing blow from a Mars-sized body. Not enough to destroy it, but enough to yank its axis over, slow its spin, and tilt it into some awkward, off-kilter orientation. Maybe it doesn't flip all the way. Maybe it just lurches. Now you have a planet that's rotating more slowly, with a strange tilt, and that makes all the difference for what gravity and tides can do next, because once a world spins slowly, it becomes much easier for tidal forces to grab hold. The sun raises tides not just in oceans, but in rock. Venus's dense atmosphere piles on its own atmospheric tides, pushing and pulling as it heats up on the day side and cools on the night side. A fast spinning planet shrugs those torques off. A sluggish, tilted Venus, it starts to drift. Its rotation can be braked, twisted, even reversed. In some simulations, Venus-like planets don't just flip once. They wander. They can slip from a quick prograde day into a slow one, stall near a standstill, then get nudged into retrograde, only to be torqued back toward prograde again. It's like cosmic tug-of-war, but in slow motion. Over hundreds of millions of years, the planet can sample multiple spin states before finally locking into a configuration where the competing torques balance out. So when you hear that Venus's day is longer than its year, and that it spins backward with an axis tilted about 177 degrees, that might not be a single smoking gun. It could be the fossil record of several different days Venus has worn in its history, each carved first by impacts, then refined by tides. A chaotic past hiding inside one very slow present. And yet something is above the planets. Something is below them. To really judge which hybrid story fits, we have to look much more closely at how Venus is spinning right now, what its atmosphere is doing, and what its interior is whispering about ancient collisions, and then compare it to the other rotational oddballs lurking in our solar system. So let's pin Venus down, right now. No theories, no ancient chaos, just how this planet has actually moved through space as you watch this video. Because here's what nobody tells you. Venus keeps time in a way that feels almost wrong. Its sidereal day, the time it takes to complete one full rotation in relative to the distant stars, is about 243 Earth days. That's longer than its 225-day year. One spin takes more time than one trip around the sun. Imagine a world where see you tomorrow means see you in 8 months. But the weirdness isn't just slow, it's backwards. If you hover above the sun's north pole and look down on the solar system, most planets spin counterclockwise. Venus doesn't. Venus turns clockwise. That's what astronomers mean when they say its rotation is retrograde. On the standard flat diagram, all the little arrows curve one way. Venus's arrow points the other way, like it didn't get the memo. Now let's begin to twist your mental picture a little more. Venus's axis isn't just tipped like Earth's. It's almost completely flipped. Earth has an axial tilt of about 23.5 degrees, which gives you seasons and that gentle wobble you've seen in every textbook animation. Venus, about 177 degrees. In plain language, its spin axis is pointed so far over that you can think of it as rotating upside down. So, is Venus really spinning backwards? Or is it just upside down spinning forwards? That's the fun part. Both descriptions are technically correct. Astronomers usually talk about the 177-degree tilt because that keeps the math consistent with the rest of the solar system's coordinate system. But for your intuition, backwards and upside down isn't a bad summary. What would this feel like on the surface if you could somehow stand on that hellish landscape and not instantly melt? The sun would rise in the west and set in the east, very, very slowly. Because the rotation is so sluggish and retrograde, the sun would creep across the sky over the course of months, tracing a path that defies everything your Earth-trained brain expects. Here's the pattern interrupt. Even that slow, backward spin isn't perfectly steady. Precise radar measurements, bouncing signals off the surface over decades, have shown that Venus's rotation rate actually changes a little with time. We're talking minutes of difference in the length of the day, but on a planetary scale, that's huge. What could do that? The leading suspect is the atmosphere. Venus's dense, super thick cloud layers whip around the planet in just about 4 Earth days, a super rotation racing far ahead of the solid ground below. As those winds slosh around, they tug on the planet through gravity and friction, trading angular momentum with the rock beneath. The result is a day length that subtly drifts. And yet, something is above the planets. Something is below them. To see how Venus ended up in this bizarre state, slow, upside down, and slightly jittery, we have to rewind the clock and ask what kind of violence, tides, and atmospheric torque could sculpt a spin this strange. So now zoom your mental camera up, off the rocks, and into the clouds. Because here's what nobody tells you. On Venus, the atmosphere doesn't just sit on top of the planet. It outruns it. High above those crushed, hellish lowlands, the winds enter a different reality. At about 60 to 70 kilometers up, the air races around the planet in just 4 Earth days. Not 400. 4. Meanwhile, the solid planet below needs 243 days to complete one slow, backward turn. The result is a world where the sky is lapping the ground over and over, like a race car endlessly overtaking a tractor that's stuck in first gear. If you could somehow float in that upper haze, you'd see the sun crawl across the sky in the wrong direction, while the cloud tops scream past you in the right direction. It's a paradox you can feel in your bones. The bulk of Venus is rotating retrograde, but its atmosphere is in what we'd call a prograde superrotation, whipping around the globe roughly 60 times faster than the crust beneath it. For a planet that already breaks our sense of what an orbit and a day should look like, this is where the picture gets properly strange. So, let's start at the very beginning of why that matters. Moving air isn't just weather, it's angular momentum on the move. Solar heating slams into the day's side of Venus's thick blanket, driving enormous atmospheric tides and waves that slosh around the planet. like a slow-motion ocean in the sky. Those tides feel the sun's gravity, and through friction with the deeper layers, they also feel the drag of the solid planet. Every push, every shear, is an opportunity to trade a tiny bit of spin between rock and air. Over millions of years, those tiny trades add up. In climate and rotation models, when you feed in a dense atmosphere like Venus's and a strong solar tide, you get torques that can subtly speed up or slow down the planet's rotation, even tweak the exact angle of that upside-down axis. Some simulations suggest that once Venus is nudged into a slow retrograde state by earlier tides or impacts, this super-rotating atmosphere acts like a constant adjustment mechanism, helping to hold the spin near its current, bizarre configuration rather than letting it drift wildly. Now let's begin to ask the bigger question. Is Venus's present-day spin just a snapshot of a delicate three-way tug-of-war? The solid planet trying to coast along, the atmosphere racing ahead, the sun's tidal pull leaning on both? If that balance shifts as the atmosphere evolves or the solar output changes, does Venus's day length slowly wander or even flip again over geological time? To answer that, we have to rewind much further, to the violent era when Venus's spin was first set and possibly shattered. That violent era didn't just leave its fingerprints on Venus. It carved scars into the spin of other worlds too. And once you see them, Venus stops looking like a lone weirdo and starts to feel like part of a much stranger family portrait. Now let's begin with the most dramatic cousin in that picture, Uranus. If Venus is spinning the wrong way, Uranus is barely spinning the right direction at all. Its axis is tilted by about 98 degrees, which means the planet is essentially rolling around the sun on its side. One pole points almost straight at the sun for decades, then trades places. Imagine Earth. But your Arctic Circle takes turns being the spot that faces the sun at noon. Because here's what nobody tells you. When you see that clean, flat diagram of the solar system, you're looking at orbits, not spins. The planets share roughly the same orbital plane, but their rotation axes can be wildly misaligned. Uranus is the poster child for that. The best explanation is brutal. In the early solar system, one or more giant impacts slammed into Uranus, knocking it over and leaving it permanently tilted. That's not a gentle nudge from gravity. That's a cosmic body check. On the opposite end of the mood spectrum, you have Mercury. Tiny, scorched, hugging the sun in a tight orbit. Mercury doesn't do the sideways roll. Instead, it plays a rhythm game with gravity. It's locked into a 3-2 spin orbit resonance. For every 2 trips it makes around the sun, it rotates 3 times on its axis. Not once per orbit like our moon, but not freely spinning like Earth either. It's a compromised state reached as the sun's powerful tides grabbed Mercury's rotation, slowed it down, and settled it into this oddly specific pattern. So in Uranus, you see violence. In Mercury, you see long, slow, tidal sculpting. Both end up with bizarre rotations. Both tell you that a planet's spin is not some sacred, permanent property. It's negotiable. Where does that leave Venus? Right in the middle, being difficult. Venus isn't tidally locked like Mercury. It's not rolling on its side like Uranus. Instead, its axis is almost fully inverted, tilted about 177 degrees, so it spins backwards, incredibly slowly, while being nearly upside down relative to the solar system's reference plane. It's like the planet tried every option and chose all of the above, but cursed. And yet, something is above the planets. Something is below them, not in space, but in their histories. Each strange rotation encodes a different sequence of impacts, tides, and internal changes. Once you see this gallery of weird spinners, you can't treat a planet's day length or tilt as background details. They're clues. So if Uranus was punched sideways and Mercury was massaged into resonance, what story is Venus's backwards glacial spin trying to tell us next? So if Uranus was punched sideways and Mercury was massaged into resonance, where does that leave Venus? To really see what its backwards glacial spin is trying to tell us, we have to do something strange. We have to imagine Venus without the hell. No crushing atmosphere, no molten plains, just a young blue world. Now, let's begin with a version of Venus you've almost never seen in a textbook. Picture it spinning the same way Earth does, prograde, with the sun rising in the east and setting in the west. The day is shorter, maybe something like tens of hours instead of 243 Earth days. The axis tilt is modest, not this upside-down 187 degrees, so seasons are gentle. Under a thinner sky, liquid water may pool in shallow oceans and lakes. From a distance, you'd point to the inner solar system and say, "Those two, they're twins." Because here's what nobody tells you. Some climate models actually support this picture. Run the simulations with a faster rotation, a milder atmosphere, and a young sun that's a bit dimmer. And Venus doesn't instantly turn into a furnace. For a while, you can get temperate conditions, clouds that reflect sunlight, and surface temperatures where water can stay liquid. Other models push back and say it heated up too fast. But that's the tension. Was there a brief, almost Earth chapter that we've completely erased from our mental picture of the solar system? If Venus did spin faster, its entire climate engine would have worked differently. A rapid rotation means stronger Coriolis forces, the invisible hand that twists winds and currents on a spinning world. Instead of the slow, lumbering super-rotation we see in Venus's atmosphere today, you'd get sharper jet streams, storm tracks that wrap around the planet, and more efficient heat redistribution from day side to night side. No permanent broiled hemisphere, no endless, stagnant twilight. So, let's start at the very beginning of how that could break. Take this balanced, Earth-like Venus and drop it into a crowded early solar system where the protoplanetary disk has just thinned out and giant impacts are still on the menu. You know the one. A Mars-sized body slams into a young world, like the event we think formed our moon. Now aim that at Venus. A single off-center collision can slow a spin, tilt an axis, even flip a planet almost upside down. A series of smaller hits can do the same thing more gradually, nudging the rotation away from its original state. Each impact doesn't just twist the axis, it jolts the climate. Oceans flash to steam, atmospheres thicken or get stripped, only to rebuild from volcanic outgassing. Once Venus's rotation slows enough, the sun's gravity and atmospheric tides can grab hold, pushing it toward the bizarre retrograde state we see today. And yet, something is above the planets. Something is below them. In this case, it's not in space, it's in time. A lost layer of Venus's history that might reveal how a world like ours crosses the line into permanent catastrophe. If Venus really started out almost familiar, then its backwards spin isn't just weird, it's the smoking gun. But what exactly pulled the trigger? Setkifin. To find the trigger, we have to go underground. Not into the clouds, but beneath the crust, into a Venus you never see in the usual flat textbook picture. Because here's what nobody tells you. The way a planet spins and the way its heart moves are tangled together. Deep inside Venus, the layout is familiar. You have an iron-rich core wrapped in a thick, rocky mantle, capped by a solid crust. On paper, it looks like Earth's interior, just scaled to an almost twin. But the dynamics? That's where the paths diverge. Earth's core is molten and churning, heat leaking outward, gravity pulling heavier elements down, lighter ones up, all of it stirred by our relatively fast 24-hour rotation. That motion turns Earth into a generator. The liquid outer core convects, charged particles spiral, and a global magnetic field snaps into place, inflating out into space like an invisible shield. It deflects most of the solar wind before it can sandblast our atmosphere. You know the one. The magnetosphere diagrams with glowing field lines wrapping the planet like a force field in a sci-fi movie. Venus doesn't have that. There's no strong global magnetic field today, just a weak, induced bubble where the solar wind itself piles up and drapes around the planet. That tells us something crucial. Either Venus's core isn't convecting the way Earth's does, or its rotation is so slow that even a convecting core can't organize into a powerful dynamo. Rotation matters here more than you'd think. Spin a conducting fluid quickly, and Coriolis forces line up the flow into columns. Perfect for building a stable magnetic field. Let that rotation crawl, and the flow becomes chaotic, tangled, unable to sustain a large-scale field. Venus takes 243 Earth days to turn once. That's slower than its year. For a dynamo, that's like trying to run a power plant by lazily swirling the turbine with your hand. So, let's start at the very beginning. What if Venus didn't used to be this slow? A younger, faster-spinning Venus could have had vigorous core convection, plus enough rotational oomph to run a proper dynamo. A real magnetosphere. Over hundreds of millions of years, tidal torques from the sun and drag from that massive atmosphere could have bled off angular momentum, first breaking the spin, then helping flip it into the retrograde state we see now. As the spin slowed and the dynamo faded, the magnetic shield would have decayed. Once that happened, the solar wind had a clearer shot at the upper atmosphere. Lighter molecules like hydrogen became easier to strip away into space, leaving heavier carbon dioxide behind and letting water vanish skyward. It's a quiet, relentless process. No single dramatic impact, just the sun's breath, unblocked. And yet something is above the planets. Something is below them. In Venus's case, what's above is that hostile solar wind. What's below is a core that might have already frozen into stillness. So the question becomes, if the interior is this quiet now, where do we look next for evidence of the violence that set all this in motion? So if the core is quiet, and the solar wind is howling above, what's left that can still twist an entire world? To answer that, we have to look at a force you already know, hiding in plain sight on your own planet. You know the one. Tides. On Earth, the moon and the sun raise gentle bulges in the oceans. Those bulges don't sit perfectly under the moon or the sun. They lag a little behind the line connecting the centers. Because Earth is spinning faster than the moon orbits, friction drags the water forward, the bulge gets pulled ahead, and gravity tugs back. That tug is an invisible hand, trading angular momentum between Earth's rotation and the moon's orbit, very, very slowly. Because here's what nobody tells you. Tides aren't just about water sloshing up a beach. They're about gravity trying to reshape a rotating world, and the world stubbornly refusing to keep up. Now let's begin translating that picture to Venus. Venus doesn't have global oceans of water, but it does have two things that can bulge and lag: a thick, hot atmosphere and a solid body that is not perfectly rigid. The sun's gravity pulls harder on the near side of Venus than the far side, trying to stretch the planet into a slightly squashed shape. At the same time, the sun's light is hammering the day side, heating the air until it surges and swells. So instead of ocean tides, Venus has atmospheric tides and solid body tides. Imagine the whole atmosphere as a slow churning ocean of gas, 90 times denser than the air you're breathing right now. As the sun rises over a region, it heats that column of air, raising its pressure. Waves of compressed, heated atmosphere race around the planet like a global heartbeat. Those are thermal tides, pressure waves locked to the day-night cycle. They don't line up perfectly with the subsolar point. They lag, they lead, they overshoot. And when those waves slide over the rugged surface, they push on it through friction and pressure gradients, stealing or donating a tiny bit of spin each cycle. Now combine that with the slower, deeper pull of the sun's gravity on the solid planet. The rock itself flexes by small amounts, generating internal friction that converts rotational energy into heat. Each misaligned bulge feels a torque. Each torque says, slow down, turn this way instead of that way. Here's the twist. Once a planet is already rotating slowly, like Venus, it becomes much easier to torque. You don't have to fight a fast spinning flywheel. You just keep nudging a lazy carousel. Over millions, then billions of years, those gravitational and thermal tides act like a cosmic brake and a cosmic steering wheel at the same time. No single dramatic impact, just the sun's light and gravity, pulling, heating, dragging, never stopping. So the real question becomes, if tides can both slow a planet and even flip the direction it spins, what exact path did Venus follow through that tidal maze? And why didn't Earth end up the same way? So that brings us to an awkward little follow-up. If the sun's tides can grind a planet down and even flip its spin, why didn't Venus just end up like a loyal, tidally locked moon, always showing the same face to the sun? Because here's what nobody tells you. Tidal locking isn't the default. It's one very specific landing spot in a whole landscape of possible spin states. And different planets walk into that landscape from very different directions. Take Mercury. You know, the one from the textbook picture, racing closest to the sun. For a long time, people thought it was locked 1-to-1, like our moon is to Earth. But radar in the 1960s revealed something stranger. Mercury rotates 3 times for every 2 trips around the sun. That 3.2 spin-orbit resonance is not an accident. It's a balance point. The planet's elongated, slightly squashed shape and its very eccentric orbit let the sun's gravity grab onto it in a repeating rhythm. So tidal torques line up and settle into that pattern. In other words, Mercury hits a groove. Every time it swings in close, the same orientation is almost facing the sun. The tidal bulge lags just right, and the net torque over an orbit adds up to 0 in that 3.2 configuration. It's like a cosmic gear ratio. Now compare that with Venus. Its orbit is nearly a perfect circle. No big speed up and slow down as it moves around the sun. No strong variation in tidal pull over each orbit. That smooth path through space erases the kind of rhythmic kick that helped Mercury lock into its resonance. So the simple 1-to-1 lock becomes just one option among many, not an obvious attractor. And then Venus adds a wild card Mercury doesn't have, an atmosphere so dense it's more like an ocean of gas. Sunlight heats the day side, the air expands and huge thermal tides roll around the planet. These are not poetic tides. They are real, moving masses of air whose gravity tugs back on the solid planet. Now let's begin to see the twist. Those atmospheric tides can push in the opposite direction to the solid body tides trying to slow and lock the planet. So instead of sliding neatly into synchronous rotation, Venus gets caught between competing torques. Models show that for a thick atmosphere on a nearly circular orbit, slow retrograde rotation can actually be a stable equilibrium. The planet's current 243-day backward spin is not just a random leftover. It's a state where solar tides in the rock and thermal tides in the air balance out. And yet something is above the planets. Something is below them. In the same way, above synchronous lock and below it, there are other stable spin states hiding in the equations. Venus simply rolled into a different valley in that landscape. So Venus didn't fail to tidally lock. It followed a different path through gravity, heat, and air, reminding us that spin evolution is exquisitely sensitive to initial conditions and environment, which raises a deeper question. If small changes can send a planet into a totally different day, how many other worlds out there are quietly spinning the wrong way too? So if small tweaks can send a planet into a totally different kind of day, you're probably wondering the next question. Could Venus flip again in? On the face of it, that sounds wild. A whole world, the size of Earth, casually changing which way it spins. But in some of the best simulations we have, that's exactly what happens to planets, with slow rotations and strong tidal influences. Their spin doesn't just gently drift. It can wander, stall, and even jump between prograde and retrograde states, like a coin that can't decide which side to land on. Because here's what nobody tells you. Once a planet is rotating very slowly, the usual stable picture breaks down. Tidal forces from the star, thermal tides in a thick atmosphere, even tiny torques from an asymmetric interior all start to compete on almost equal footing. You get what dynamicists politely call chaotic spin evolution. In plain terms, the axis can tilt, the direction can reverse, and the length of the day can stretch or shrink over time. So where does Venus sit in that landscape right now? Is it finally resting in a stable rotational equilibrium, or are we just catching it in a long, drawn-out metastable phase? We see a retrograde spin of about 243 Earth days, a tilt of roughly 177 degrees, and an atmosphere that's more than 90 times Earth's surface pressure. That combination looks suspiciously like the kind of system that can hover near balance, then slowly slide into a new configuration over millions or billions of years. You know, the one comparison that helps here, Mercury. It's locked into a 3.2 resonance with its orbit, a very clear, stable end state. Venus doesn't have that neat commensurability. Instead, its equilibrium is set by a tug of war between solid body tides trying to slow and align it one way, and atmospheric tides powered by sunlight trying to twist it another. Change either side of that tug of war, and the balance point moves. And yet, something is above the planets. Something is below them. For Venus, those above and below layers are not just poetic. They're mechanical. A small change in atmospheric mass, a shift in cloud patterns that alters how heat is absorbed, or a reorganization of the interior, say, the core cooling and solidifying differently, could in principle nudge the torque budget. Even a slight tweak to its orbit from long-term gravitational interactions in the solar system could matter, because the sun's gravity sets the rhythm that all those tides dance to. Now let's begin to temper the drama. These aren't changes you or your great-great-grandchildren will notice. We're talking timescales from tens of millions to billions of years, with Venus's day length creeping, pausing or drifting rather than suddenly flipping like a coin. But the key idea is that planetary spins are not eternally fixed. They're more like slow-motion experiments in celestial mechanics. So if we want to know whether Venus is truly done evolving or just mid-flip in geological slow motion, we need better data. We need to see its interior structure, read the erased chapters on its surface, and untangle the detailed dynamics of that super-rotating atmosphere. And that's where the next generation of missions steps in, with radar, probes, and orbiters that might finally tell us which way Venus is really heading. So the story shifts. We've stared at blurry radar maps and puzzling spin measurements for decades. Now the question becomes, who's actually going to walk up to Venus, knock on the door, and ask what happened? Enter the Venus detective team. First on the scene is Veritas, NASA's planned orbiter. Think of it as the planet's full-body scan. It will fire radar down through the clouds to build global maps of the surface at resolutions we've never had before, and at the same time it will track tiny wobbles in its own orbit to read Venus's gravity field. That combination lets us weigh the interior, see how thick the crust is, and spot subtle deformations that tell you whether the mantle is still churning or mostly frozen. Because here's what nobody tells you. To explain a planet's spin, you have to know what's inside. A world with a sloshy core and an actively convecting mantle responds to impacts, tides, and atmospheric torques very differently from a stiff, cooled down one. If Veritas finds that Venus's interior is still flexing, still reshaping the surface with fresh volcanism, that supports models where its rotation has been evolving over billions of years, not just locked in by one ancient catastrophe. Then Europe sends in a partner. ESA's Envision orbiter will fly later, sharing the same crime scene but bringing a different toolkit. It will also use radar, but tuned to zoom in on specific regions, searching for buried tectonic patterns, old subduction-like zones, and young lava flows. On top of that, it will watch the atmosphere from above, tracing how energy and momentum move from the dense lower layers up into the fast, super-rotating winds. You know the one. That bizarre upper atmosphere that laps the planet every 4 Earth days while the surface crawls through a 243-day rotation. Envision lets us ask where those winds get their power and how strongly they tug back on the solid planet. If those atmospheric tides are big enough, they could have helped flip Venus from a normal prograde spin into the slow retrograde state we see today. And then comes the most dramatic move. NASA's Da Vinci mission doesn't just orbit, it dives. A probe will plunge straight through the clouds, sampling the atmosphere's chemistry, temperature, and winds all the way down to the surface. It's a one-way trip, but in that descent you get the vertical profile of the entire air column. So, let's start at the very beginning of Venus's biography. Isotopes of noble gases, traces of water, the exact layering of pressure and temperature. Da Vinci turns those into timestamps. Did Venus lose its oceans early, making the atmosphere thick enough, soon enough to torque the spin over eons? Or did a giant impact do the initial twisting, with the atmosphere just finishing the job? And yet, something is above the planets. Something is below them. In this case, it's the full 3-dimensional structure of Venus itself, from core to cloud tops, finally coming into focus. Put Veritas, Envision, and Da Vinci together, and within a few decades, we won't just be guessing between giant impact and slow tidal flip. We'll be able to rule scenarios out, to say which histories match the geology, the interior, and the air, or confront a wild new picture where Venus's backward spin is only one chapter in an even stranger rotation story. And the twist is, that verdict won't just rewrite Venus. It will force us to rethink how fragile the spins of Earth-like worlds really are across the entire solar system and beyond. So if the atmosphere and the interior are both whispering clues about Venus's spin, the surface is where those whispers turn into scars. This is the only place we can actually see the record. Frozen, fractured, and strangely young. Because here's what nobody tells you. For a planet that's been around for 4.5 billion years, Venus's face looks suspiciously fresh. When we count impact craters and radar images, we don't see an ancient, crowded battlefield like the Moon or Mercury. We see a modest number of craters, spread almost randomly across the globe, with very few that are half erased. That pattern screams that something dramatic resurfaced most of the planet in the last billion years or so. That's weird. It means most of the rocks we're looking at are geologically recent. Even if recent still means hundreds of millions of years. So, what did the resurfacing? And what does that have to do with rotation? Look closely at those craters, and they're not just potholes in a flat parking lot. Some are pristine bowls, others are squashed, fractured, or partly flooded by lava plains. A few sit on top of gentle rises, or are sliced by faults and rifts. Each deformation is a tiny seismograph, a record of how the crust was stretching, compressing, and flowing after the impact. If a crater has been pulled apart, you know the surface was under tension. If it's been buried by lava, you know volcanism stayed active long after the rock first formed. And volcanism plus tectonics means interior heat trying to escape. That heat drives mantle convection, great, slow currents of rock that can drag the outer shell around, create rift zones, and inflate bizarre circular features called coronae. You know the one, those ring-like scars that look like someone pressed a hot coin into the crust and then twisted. Now let's begin to connect that to spin. Rotation changes how convection patterns organize. A fast spinning planet gets strong Coriolis forces that break flows into bands and cells. A slow lumbering rotator like Venus feels those forces much less. So convection can arrange itself differently, concentrating stresses in particular belts or patches. Coronae chains, global rift systems, and broad highlands might be the frozen fingerprints of that interior circulation, shaped in part by how quickly and in what direction the planet was turning. Here's the dream scenario. If we can date different lava plains, tessera highlands, and cratered terrains, and if we can tell which came before or after key tectonic episodes, we could line those ages up with models of how Venus's spin and axis tilt evolve. Did the big resurfacing pulse happen while Venus was still spinning prograde, or after it had already flipped into its current retrograde state? Because once you ask that, a sharper question appears. Did a late giant impact both scramble the spin and trigger a catastrophic resurfacing, boiling the mantle and paving the crust? Or did tides and atmospheric torques slowly reverse the rotation first, with internal processes and gravity-driven overturns erasing the surface long after the spin had settled? To answer that, we need more than blurry radar maps. We need to go back and read the scars in person. So if the surface is hiding its past, we look where Venus can't cover its tracks. Up, into the air that never stops moving. Because here's what nobody tells you. The weirdest part of Venus's rotation isn't at the ground at all. It's above the clouds. Down at the surface, you'd be crushed under an atmosphere more than 90 times Earth's pressure, a dense ocean of carbon dioxide and nitrogen that crawls around the planet in sync with that 243-day spin. It's thick, hot, and almost locked to the rock beneath it. Climb a few dozen kilometers and the picture changes. By about 45 to 50 kilometers up, you hit the famous cloud decks. Global blankets of sulfuric acid droplets, stacked in layers that turn the whole planet into a glowing, featureless ping-pong ball from space. These clouds aren't just decoration. They're the boundary between the slow world below and something much stranger above. Keep going to 60 or 70 kilometers altitude, and the atmosphere snaps into a different regime. Up here, the winds race around the planet in just about 4 Earth days. Remember, the solid planet underneath takes 243 days to turn once, so the air is lapping the ground roughly 60 times faster. If you could float at that height, the sun would still rise in the west and set in the east, but the sky around you would scream by like a global jet stream on fast forward. This is superrotation. The entire atmosphere circling much faster than the planet that carries it. We've seen hints of it on Titan, on Earth's equatorial stratosphere, even in some exoplanet models. But Venus is the poster child, and yet something is above the planets. Something is below them. Here, the above and below are vertical layers in the same air column, each with its own relationship to the spin. So what's pushing that upper atmosphere so hard? So, let's start at the very beginning of the mechanism. One idea is that waves generated lower down. Gravity waves from air flowing over surface highs and lows, and planetary scale Rossby waves propagate upward and break like ocean waves on a beach, dumping angular momentum into the high altitudes and accelerating the flow. Another key suspect is thermal tides, daily heating and cooling of the thick atmosphere by sunlight that sets up giant pressure waves. Those tides can drag air toward the equator and upward, redistributing angular momentum until the whole upper atmosphere locks into this 4-day sprint. Now let's begin to connect this back to the solid planet. All that fast-moving air is rubbing against the slower layers below and through them, against the surface. Friction, pressure differences, and even tiny topographic bumps can transmit torque back into the crust. Over millions or billions of years, could that feedback help break or even flip the spin of the planet itself? That's not just a Venus question. When we look at exoplanets that rotate slowly, or even backwards, and we see bizarre wind patterns in their spectra, we're really asking, how tightly are the rocks and the air holding hands? To answer that, we need to watch Venus's atmosphere in exquisite detail and see exactly how a slow, backward spinning world teaches its sky to run laps. So if Venus is our local laboratory for slow, backwards worlds, the obvious question is, where are all the other Venuses hiding? Because here's what nobody tells you. Most of the exoplanets we've found so far don't look like neat copies of Earth at all. They huddle brutally close to their stars, packed into orbits so tight that a year can be a few days, or even a few hours. In that furnace, tidal forces are relentless. Gravity doesn't just hold the planet in orbit. It grabs the spin, breaks it, and can lock one side to permanent day while the other freezes in endless night. We already see this in action. Many small, hot exoplanets are probably tidally locked, like a whole galaxy of supermercuries and supermoons. But push the tides harder, mix in a thick atmosphere, and the picture gets weirder. A planet can get trapped in slow rotations, strange spin-orbit resonances, or even end up rotating retrograde, with the star rising in the west, like on Venus. So when you look at a catalog of close-in rocky worlds, you're not just seeing alien planets. You're seeing a menu of possible Venus outcomes. And then there are the drama queens of exoplanet science. Hot Jupiters, giant planets, often bigger than Jupiter, whipping around their stars in just a few days. Some of those orbits aren't just tilted, they're flipped. We've measured systems where the planet's orbit is highly inclined or even retrograde relative to the star's spin. You know, the one textbook picture where everything orbits in a tidy, flat plane. These worlds ignore that memo completely. Those wild orbits are a warning label. They tell us entire planetary systems can be dynamically disturbed by migrating giants, passing stars, or the leftover chaos of formation, hard enough to twist or flip both orbits and spins. If a Jupiter can be thrown onto a backwards orbit, what could that do to an Earth-sized neighbor sharing the same space? Now let's begin to use Venus as our decoder ring. We model Venus's spin evolution, giant impacts, long tidal braking, atmospheric torque. We're really building a toolkit for exoplanets. Take an Earth-mass world close to its star, give it a dense, hot atmosphere, and our Venus-inspired equations say slow rotation is likely. Retrograde rotation is on the table. Super-rotating winds that lap the planet in a few days, racing far ahead of the surface, are not exotic at all. They're expected. So somewhere out there should be exovenuses. Rocky planet with thick skies, snuggled up to their stars, turning so slowly that their atmospheres run circles around them. And yet, something is above the planets. Something is below them. We see spectral hints of fierce winds, day-night temperature contrasts, clouds shifting across the terminator, but we don't yet see the spin directly. The real cliffhanger is simple. When we finally measure the rotation of true Earth-like exoplanets, will Venus's strange, slow, backward spin turn out to be the cosmic oddball, or the rule we should have expected all along? So before we call Venus the oddball of the solar system, we have to ask a slightly uncomfortable question. Is there actually a right way for a planet to spin? On every diagram you've ever seen, Venus is tagged as retrograde, as if it's misbehaving while the other planets politely follow the rules. Because here's what nobody tells you. That judgment quietly assumes there is a standard direction, and that standard is baked in before the planets even exist. When the original molecular cloud collapsed, it didn't just fall inward, it swirled. That gave the newborn disk, and then the sun itself, a preferred spin. Astronomers look at the way the sun rotates, look at the direction the planets orbit and say, all right, that's prograde. That's the positive direction. You know the one. Counterclockwise if you hover above the sun's north pole in your mental picture. Anything that spins the other way gets stamped retrograde. Venus. Uranus's weirdly tilted seasons. The occasional backward orbiting asteroid. But here's the pattern interrupt. What if we had defined the opposite direction as positive? Flip the sign on the whole solar systems. Suddenly, the majority of planets become the rebels. Their spins are retrograde, and Venus is the quiet, well-behaved one. Same physics, same orbits, same gravity. Only the label changed. So is Venus really wrong? Or did we just choose a team and color its jersey blue instead of red? To keep all this straight, astronomers use something a bit more formal than "this feels right." They define a planet's north pole using the right-hand rule. curl the fingers of your right hand in the direction the planet spins, and your thumb points to its north. Then they compare that thumb to the sun's spin axis. If the thumb points roughly the same way and the planet rotates the same way it orbits, that's prograde. If it points the other way, like Venus's nearly upside down 177-degree tilt, we file it under retrograde. So yes, by that convention, Venus is spinning backwards. But notice the word convention. A choice, a reference plane, and a reference spin we agreed on, not a cosmic law carved into space. What actually matters, physically, is how a planet's spin lines up with the environment it formed in and what that mismatch whispers about its past. Did gravity nudge it gently over billions of years? Did a giant impact slam into it and flip it? Did a dense atmosphere, like Venus's, slowly torque the rotation until it reversed? Those questions are about history, not morality. Venus isn't misbehaving, it's simply telling a different story than the one we expected from our flat, tidy diagrams. And once you stop asking, is this the right way to spin? You can finally ask the real question: what had to happen to twist a world this far from its original script? So let's take that twisted script and drop you right into it. You're standing on a hypothetical Venus that's been terraformed just enough for you to walk outside in protective gear, with breathable air pumped into your suit. The pressure isn't crushing, the temperature won't melt lead, and for once, the horizon isn't hidden behind toxic cloud. You look up. You know the one thing you're waiting for: sunrise. But this world has other plans. On backward spinning Venus, the sun doesn't pop up over the eastern hills before you finished your coffee. It crawls into the sky from the west. Very slowly. Because here's what nobody tells you: a single Venus day is longer than its year. So you could stand there for weeks, watching the sun inch upward, barely changing its angle from one Earth day to the next, like someone pressed slow motion on the sky. Dawn isn't a moment here. It's a season. The light goes from deep indigo to orange over many Earth days, shadows stretching and twisting at a pace your Earth-trained brain can't quite accept. You go to sleep, wake up, work, relax, lose track of time, and the sun has moved. A little. On this world, what time is it is the wrong question. You'd be asking, which part of the day season are we in? Now, let's begin to imagine daily life pinned to that kind of rotation. Your circadian rhythm is useless. No one is trying to stay awake for a 243 Earth day and then sleep through a 243-day night. So society breaks the link. Clocks run on some artificial 24-hour cycle, while the sky above ignores them, drifting from endless sunrise to endless noon to endless sunset over months. Holidays aren't tied to dates. They're tied to phases of the sun's crawl. Agriculture turns inside out. Fields on the long dawn side soak in gentle, low-angle light for weeks, perfect for certain crops, while the far side is locked in a long, cooling dusk. You might rotate farming zones around the planet, chasing that sweet spot before the sun beats down for month-long midday. And yet something is above the planets. Something is below them. Here, that abstract idea of latitude on a spinning sphere suddenly feels personal, because your entire food supply depends on where you sit in the slow dance between day and night. What about weather? With such a slow spin, one side of the planet would tend to bake while the other chills, creating brutal temperature contrasts. But a thick atmosphere and powerful winds, like the super-rotation we actually see on Venus, would smear heat around the globe, whipping clouds around in just a few Earth days while the surface lags behind. The sky would feel fast even while the ground feels frozen in time. So, let's start at the very beginning of the real story. Our Venus doesn't offer gentle dawns and leisurely sunsets. It offers a hellscape. Yet this thought experiment nails one thing into your memory. Its day isn't just slow, it's backwards, alien to our neat solar system picture. Which raises the next question. What kind of violence and invisible forces does it take for gravity to twist a world into that kind of schedule? To answer that question, we have to admit something uncomfortable. The picture in your head has been quietly lying to you. Because here's what nobody tells you. Every diagram you've ever seen of the solar system is making a choice about what to tell the truth about, and what to flatten, hide, or ignore. When we draw those neat circles on a flat page, with identical little arrows all pointing the same way, we're shouting about orbital order and whispering about spin. You get Mercury, Venus, Earth, Mars, all lined up like beads on a wire. And your brain learns one lesson. Everything goes around the sun in a simple, orderly way. Now let's begin with that classic classroom poster. You know the one. The sun in the middle, planets in perfect rings, maybe a few moons, maybe an asteroid belt for spice. Those arrows hugging each orbit, they're really just saying, forward. They almost never bother to show that Venus's arrow should curl the opposite way, or that Uranus's spin axis is lying almost on its side like a rolling ball. The diagram has already decided. Orbits matter more than rotations. Textbooks do the same trick with tilt. Earth gets a cute little 23.5 degrees lean, maybe with seasons drawn in. But if we showed axial tilts to scale, Venus's axis would be nearly upside down at 177 degrees, and Uranus would be practically horizontal. That would look messy. It would ruin the clean geometry. So the weirdos get rounded off visually until your intuition thinks, sure, everything's more or less the same. Is it any wonder that Venus's backwards day feels like a glitch instead of a clue? There's another quiet lie hiding in those images. Time. We freeze the solar system as if it's a finished machine, not an ongoing accident. Those orbits look timeless, like they've always been there and always will be. But the real story is billions of years of chaotic evolution, collisions, near misses, migrating planets, and shifting spins. A single frame on a page has no way to show you Mercury being captured into a spin-orbit resonance, or Venus's rotation being torqued and twisted over eons by tides and atmosphere. And yet, something is above the planets. Something is below them. Not just in space, but in history. Layers of violence and subtle gravity games that never make it into the flat picture. This isn't malicious. It's a teaching strategy. We simplify to get you in the door. But the price of that simplicity is a brittle mental model that cracks the moment you meet an oddball like Venus. So let's start at the very beginning of fixing that. From now on, when you see a diagram, treat it as a starting point, not a final truth, and ask, what motion is missing? What history is erased? What three-dimensional chaos has been ironed into that tidy plane? Because once you start asking those questions, Venus's wrong-way spin stops being an exception and starts being a warning that the solar system you learned is only the first draft. And the next draft, that's where the real violence shows up. So if the first draft solar system is that neat, flat classroom diagram, the next draft does something uncomfortable. It lifts you up, out of the page and asks, what does above and below even mean around Venus when space itself has no up or down? Because here's what nobody tells you. When we say something is above or below Venus, we're not talking about some cosmic ceiling or floor. We're talking about directions that are perpendicular to an agreed upon flat sheet, the average orbital plane of the planets, the same basic plane Venus orbits in. You know the one. In that picture, above Venus just means on one side of that sheet. Below means the other side. Flip the sheet, and you flipped what counts as up. Now let's begin to thicken that sheet. Venus's orbit is almost in the same plane as Earth's, but not perfectly. Mercury is tilted, Mars is tilted, even Earth is slightly tilted relative to the average. Each orbit is like a ring that's been nudged a few degrees off the table. Tiny angles, sure, but over tens of millions of kilometers. Those tiny angles send planets millions of kilometers above and below that reference plane. Already the solar system is not truly flat. It never was. Then we add asteroids. Main belt rocks swing around the sun at 10, 20, 30 degrees to Venus's orbit. Some comets plunge in almost vertically, their paths slicing straight through the planetary plane like thrown spears. A few strange bodies even orbit backwards, looping opposite the planets. And yet something is above the planets. Something is below them. It's a whole thickened cloud of orbits, layered and crossing, a three-dimensional web held together by gravity. Keep zooming out and that web turns fuzzy. Beyond Neptune, Kuiper Belt objects and scattered disk worlds like Eris are tilted so wildly that the idea of one privileged plane starts to fall apart. Push farther still and the structure changes again. The Oort cloud, the distant reservoir of long-period comets, isn't a disk at all. It's a roughly spherical swarm of icy bodies, stretching out thousands, then tens of thousands of times farther than Venus is from the sun, wrapping the solar system in all directions. From far away, the whole thing looks less like a record and more like a very flattened, very fuzzy sphere of material. Venus's orbit is just one thin slice through that sphere. Its spin axis, just one arrow in a forest of arrows, pointing every which way as orbits tilt, scatter, and evolve over billions of years. So in a system where paths can twist out of the plane, where comets fall in from every direction, is it really shocking that a planet's spin could end up flipped, even reversed? Venus isn't breaking the rules. It's following the same three-dimensional chaos as everything else. Which raises the real question: what, exactly, twisted Venus so hard? A single catastrophic blow, or slow, relentless forces that turned it upside down over eons? So if Venus can be flipped in its own little neighborhood, how big does the neighborhood have to get before backwards stops meaning anything at all? To see that, we have to zoom out, way out. Now, let's begin with the units your brain already knows from those textbook diagrams. Venus orbits at about 0.72 astronomical units from the Sun. 1 AU is the distance from Earth to the Sun, so Venus is tucked well inside Earth's path, circling along with the other planets in that familiar, relatively thin disk. You know the one. The neat, flat picture with orbits like rings on a target. At this scale, the solar system feels organized. There's a clear plane, the ecliptic. Venus's orbit hugs that plane tightly, only slightly tilted. So, above and below still sound reasonable, like you could pick a side of the disk and label it up. But that's only because we're still thinking in single digits of AU. Push the camera back to hundreds, then thousands of AU, and that tidy disk starts to blur. Out here, we're in the realm of the Oort cloud, where the sun's gravity barely hangs on to a vast swarm of icy bodies. Their orbits are tilted at every angle, forming a roughly spherical halo that may extend to around 100,000 AU. At this point, what would the orbital plane even mean? Which way is up? When comets are falling in from almost every direction at once. Because here's what nobody tells you. The planetary disk that makes our solar system look flat is just a thin scratch inside a much larger three-dimensional cloud of orbits. The ecliptic is a local rule, not a universal law. Zoom out again until AU stop being convenient and you have to switch to light years. The entire Oort cloud, Venus, the sun, all of it, shrinks to a tiny bubble embedded inside the Milky Way's galactic disk. That disk is about 1,000 light years thick and 100,000 light years across, a flattened cloud of hundreds of billions of stars. Now the question becomes, what plane are we talking about? The solar system's orbital plane is tilted by about 60 degrees relative to the Milky Way's disk. As the sun orbits the galaxy, it doesn't ride perfectly in the mid-plane. It bobs up and down through the galactic disk over tens of millions of years, like a ship rising and falling on a very slow, very shallow, cosmic swell. In this layered picture, there is no master up, no final down. There are only planes on top of planes, orbits nested inside orbits, each with its own convenient zero line. Venus's backward spin. It's just one tiny, crooked arrow in a vast, rotating cloud of motions, all leaning and twisting in their own directions. So the real mystery isn't why Venus broke some cosmic alignment. It's how, in all this swirling geometry, any planet ends up looking orderly at all, and that's where we go next. So when we say Venus is spinning the wrong way, whose wrong are we actually talking about? Yours, mine, the version of direction wired into a brain that grew up glued to one particular planet, under one particular pull of gravity. On Earth, your whole sense of space was trained by falling. There's the ground that stops you, the sky you can't reach, the way your inner ear screams when those two get swapped on a roller coaster. Up is away from Earth's center, down is toward it. Simple, predictable. Your body loves that. Because here's what nobody tells you. Your intuition about direction is basically a souvenir from a very specific survival problem. We carried that souvenir into the solar system. We draw a flat line through Earth's orbit, call it the ecliptic plane, and suddenly, that looks like the right way for everything to move. Planets that orbit and spin in that same general sense. Normal, comforting. Anything that leans too far or spins backwards feels like it's breaking a rule you were sure existed. But in space there is no up, there's no down. There are only choices. We decide the sun's north pole is up because its rotation points that way relative to the stars. We define the ecliptic plane because Earth's orbit is convenient. We pick the galactic plane because the Milky Way is a bright, obvious band in the sky. None of those planes came with cosmic labels glued on. We wrote the labels ourselves. Astronomers are very open about this cheat code. They build coordinate systems the way you might pick a camera angle, whatever makes the picture easiest to understand. You want to talk about planets? Use the ecliptic. You want to talk about the galaxy? Rotate your mental grid until the Milky Way's disk is your new zero. Need to map the whole sky. Switch to a system tied to Earth's poles. The universe never flinches, because it doesn't care which grid you choose. Now drop Venus into that. From the vantage point where the sun's spin and the original protoplanetary disk define normal, Venus's rotation is retrograde, tilted about 177 degrees, almost upside down. The sun would crawl across the Venusian sky from west to east. Weird, right? But rotate your coordinate system so Venus's spin axis is your reference, and suddenly it's the hero of the story. And most other planets are the ones doing strange, tilted gymnastics. So, let's start at the very beginning of this discomfort. It's not that the cosmos is chaotic. It's that our expectations are provincial. And yet, something is above the planets. Something is below them. Not because space respects those words, but because we keep inventing new planes to slice through the same three-dimensional reality. If that feels disorienting, good. That wobble in your mental picture is where the fun starts. Once you stop expecting the universe to line up with your inner ear, you can ask a sharper question. Not, which way is up, but which choice of up reveals the most. Stay with that, because in the next part we'll use Venus's twisted spin to dig into what actually did that twisting in the first place. That which choice of up question becomes deadly serious the moment we try to describe how a planet spins. Because here's what nobody tells you. Before you can say whether Venus is rotating the wrong way, you have to decide what right even means. You have to build a coordinate system out of thin air. That means picking a north pole, drawing an equator, and choosing some direction on the sky as your zero line. None of those are carved into space by gravity. They're conventions, useful ones, but still choices. So, let's start at the very beginning. If you lived on Venus, which pole would you call north? The one where the sun appears slightly higher? The one that matches Earth's orientation? Or the one that lines up best with the rest of the solar system? Astronomers needed a rule that worked for every world, from Mercury to the weirdest, distant dwarf. So the International Astronomical Union made a decision. A planet's north pole is the one that lies above the invariable plane of the solar system, the average plane of all the planets' orbits. You know the one, the invisible sheet that Earth's orbit, the ecliptic plane, sits inside, and that we quietly use as the baseline for almost every flat diagram you've ever seen. Look at Venus with that rule, and its axis is tilted by about 177 degrees. In other words, relative to that shared orbital plane, Venus is essentially upside down. Its geographic north pole, by definition, points to the same side of the invariable plane as the sun's north pole. But the planet's surface is rotating in the opposite direction to most planets when you watch from that vantage point. Here's the twist. If you flip your viewpoint and stand on Venus's own axis, treating that upside-down orientation as normal, the planet is actually spinning prograde. It turns in the same mathematical sense as its orbit around the sun. Prograde relative to itself, retrograde relative to the sun's spin, and almost every other planet. Same motion. Two equally correct descriptions. Which one sounds more dramatic to you? And yet, something is above the planets. Something is below them. Not in any absolute sense, but in the sense that we quietly picked a plane, drew an arrow, and declared, "This way is up." That framing lets us call Venus an oddball, a rule breaker, a planet that spins backwards. It also hides the fact that we could have chosen a different framing where Venus is the one that's normal and everyone else is the one tilted the other way. Good science communication doesn't pretend those choices don't exist. It surfaces them. It tells you not just what Venus is doing, but which coordinate system we're using and why. Because once you see the coordinate grid behind the language, you're ready for the deeper question. What physical events twisted Venus into this orientation in the first place? That's where we're heading next. Once you start asking what twisted Venus into this bizarre orientation, a darker realization creeps in. This isn't just a weird spin story. It's a warning label hanging off every so-called Earth-like world we discover. Because here's what nobody tells you. Venus and Earth started out as near twins. Same solar system, same protoplanetary cloud, orbits in almost the same plane, almost the same size and mass. From far away, in that flat textbook picture, you'd circle both and write habitable zone with a hopeful little question mark. And yet one ended up with oceans and forests, while the other turned into a pressure cooker with a backwards day. So what broke the symmetry? Tiny differences that snowballed. A slightly different initial spin, a different sequence of giant impacts early on. A different tidal environment as gravity from the sun, and later that monstrous atmosphere slowly torqued the planet's rotation. You change the spin rate a bit. You change how heat is moved around. You change how long day and night last. You change how clouds form, how water stays liquid or boils away. On Venus, that feedback loop ran off a cliff. A runaway greenhouse thickened the air until the surface pressure crushed down over 90 times harder than Earth's. That dense atmosphere didn't just trap heat, it pulled on the planet itself. Atmospheric tides and solar tides worked together for billions of years, breaking and twisting Venus until its spin slowed, stalled, and flipped into retrograde. The sun now crawls from west to east across a sky hot enough to melt lead. Being in the right place around the star clearly wasn't enough. So let's start at the very beginning of our exoplanet fantasies. When we say exo-Earth, what do we really mean? A rocky planet, Earth-sized, and the habitable zone, with a nice circular orbit. You know the one, the blue marble on the artist's poster. But from light years away, an exovenus can look almost identical. Same orbit, same radius, same mass. The spectrum just tells you there's an atmosphere. It doesn't automatically tell you if that atmosphere is a gentle sky or a 500-degree sulfuric acid nightmare wrapped around a slowly spinning backwards world. And yet, something is above the planets. Something is below them. There's a whole probability cloud of possible histories hovering over every Earth-like orbit. And Venus shows us how easily that cloud can collapse into hell instead of home. Now, let's begin to treat Venus not as a curiosity, but as calibration. If we can decode exactly how it crossed the line from habitable to hostile, we're not just explaining one planet's weird spin. We're mapping the razor-thin boundary that decides which worlds can keep oceans, and which worlds burn them off. In the next section, we'll follow that boundary back in time and ask, what did Venus's earliest days look like? Before the flip, before the furnace. So if Venus's earliest days hold the secret, can we just rewind the tape and watch? Not quite. There's no cosmic CCTV for the inner solar system. No frame-by-frame replay of every collision, every tidal tug, every atmospheric shove that twisted this world's spin. Because here's what nobody tells you. For a planet like Venus, a perfect biography is impossible. Over 4.5 billion years, impacts erase impacts. Heat flow reshapes the interior. The atmosphere thickens, thins, and thickens again. By the time we show up with radar and orbiters, most of the obvious fingerprints are gone. All we have left is the crime scene as it looks today. So instead of hunting for one cinematic, slow-motion impact we can point to and say, that's the shot, scientists do something subtler. They build families of possible histories. Different starting spins, different sizes and angles of collisions, different strengths of tidal breaking from the sun, and torques from that crushing atmosphere. Then they ask a simple but brutal question. Which of these paths could actually land us on the Venus we see now? You know the one, retrograde rotation, a day longer than its year, an axis tilted a dizzying 177 degrees, wrapped in an atmosphere so dense that high-altitude winds lap the planet every 4 Earth days while the surface crawls beneath. Any model of Venus's past has to thread all of that at once. Miss one detail, and gravity, chemistry, or basic mechanics will tear your elegant idea apart. This is where every new data point matters. A sharper gravity map from an orbiter doesn't just make a prettier picture. It tells you how mass is distributed inside, which in turn tells you how easily Venus could have been tipped or spun down. A more precise profile of the atmosphere's temperature and winds that tightens how strong atmospheric tides can be and how much they can speed up or slow down the rotation. Each measurement rules out whole branches of the what-if tree and quietly boosts the odds of others. Did one catastrophic impact dominate, flipping Venus almost upside down in a single bad afternoon, or did a long series of smaller hits, followed by billions of years of tidal breaking, gradually shepherd its spin through a chaotic dance into the strange retrograde state we see now? How stable is that state? Is Venus perched in a delicate balance where small changes in its atmosphere could nudge its day length? Or is it locked in tight? And yet, something is above the planets. Something is below them. The atmosphere isn't just a hazy blanket. It's a moving engine, exchanging angular momentum with the interior through friction and waves. How tightly are those two layers coupled? Could shifts in atmospheric circulation subtly torque the solid planet over millions of years? Or is the mantle calling all the shots while the clouds just race along on top? Now let's begin to pull back and look at the next few decades. Missions like Veritas and Vision and Da Vinci won't give us a neat, one-sentence origin story. They will, however, corner Venus. Better maps of its surface age, better constraints on its interior, and direct dives through its atmosphere will force us to throw out pet theories and rebuild our mental model from the ground up. So will we ever know Venus's exact spin story, moment by moment? No, but we're on track to know which stories are impossible, which are merely unlikely, and which narrow pathways through the chaos could actually have happened. And the real twist is this: when those new results arrive, they won't just rewrite Venus. They'll reach back into the solar system's earliest cloud of gas and rock and change what we think happened to every young world that tried to spin. In the next sections, we'll walk into that cloud and watch those worlds form, and you'll see why Venus's wrong way rotation might be the most honest record we have of how violent those first orbits really were. So let's step back from that violent cloud for a moment and look at the picture in your head that all of this is trying to replace. You know the one. The classroom poster where the solar system is a perfect, flat, glowing disk. The planets are marbles on a table, and every world glides around the sun in the same neat plane, spinning in the same tidy direction. It feels orderly, clockwork, almost polite. Because here's what nobody tells you. That poster is less like a photograph and more like a map of a subway line. Useful, clean, and absolutely ruthless about what it leaves out. It hides the fact that rotation is fragile. It hides the violence, and it hides the slow, patient forces that keep tugging on those spins long after the chaos of formation is over. So, let's start at the very beginning of the corrections we've made. In that early cloud, giant impacts didn't just build planets. They scrambled their rotations. A Mars-sized body can hit an Earth-sized world, and tilt it, slow it, even flip it. Then once the fireworks calm down, the quiet forces move in. Tidal forces from the sun and from moons act like brakes, draining spin energy. Thick atmospheres raise tides in the air itself, and those tides push back on the planet, adding tiny torques over billions of years. Given enough time, normal rotation is more of a suggestion than a rule, and while all this is happening, the geometry you learned gets messier too. The solar system is not truly flat, even close in. Each planet's orbit is tilted a little off the ecliptic plane, so those marbles don't all sit on the same table. They weave above and below it by millions of kilometers. Push farther out, and the Kuiper belt thickens that picture. With icy worlds on steeply inclined or even retrograde paths. Beyond that, the Oort cloud isn't a disk at all, but a vast, roughly spherical swarm. In space, there is no up, there is no down. There is only above and below some planes we chose to draw. And yet, something is above the planets. Something is below them. Not because the universe prefers a direction, but because gravity, collisions, and time have puffed our once flat disk into a three-dimensional, evolving structure. In this richer model, Venus becomes the emblem, a near twin of Earth in size and orbit that ended up almost upside down, rotating backwards, with a day longer than its year. Its slow retrograde spin is not an error, it's a fossil. Encoded in that wrong-way rotation are the fingerprints of early impacts, relentless tidal braking, and an atmosphere so massive it can torque an entire world. So when you visualize the solar system now, don't see a tidy diagram. See a layered, three-dimensional ballet of worlds, each on a slightly different track, each with its own rotational biography. In the next section, we'll zoom back into that ballet and watch how those first spins were handed out in the disk itself, and why Venus's bizarre day might be the most revealing orbit of all. So here's the upgrade we're quietly sneaking into your brain. From now on, Venus isn't just that hot planet with clouds. It's a built-in alarm system for bad diagrams and oversimplified stories. Next time you see that neat, flat solar system picture in a textbook or on a website, pause for half a second. You know the one. Perfect circles, tidy labels, all the arrows going the same way. In your head, ask one question. Where's Venus's backward spin in this picture? If the answer is nowhere, what else might be missing? Are we seeing orbits but not rotations? Are we seeing the plane but not the vertical thickness? That tiny habit turns you from a passive viewer into someone quietly auditing the universe. Because here's what nobody tells you. The weird cases aren't side notes, they're the stress tests. When we say planets form from a rotating cloud and line up in a disk, that idea has to survive contact with Venus's retrograde spin. Uranus rolling around on its side, and Mercury locked into a strange spin-orbit resonance with the Sun. If your model can't explain the oddballs, it isn't a complete model, it's a draft. Think about how this plays out. Venus is upside-down rotation, Uranus is 98-degree tilt. Mercury's 3-2 spin-orbit lock. They're all like glitches that force us to check the code. Did giant impacts rewrite their spins? Did long-term tides and atmospheric torque slowly twist them into these positions? When simulations fail to reproduce those outliers, we don't throw out the planets. We refine the physics. So when you hear about a new exoplanet system, 3 hot Jupiters, or a world tidally locked to its star, bring this flexible, 3-dimensional mental model with you. Don't imagine a flat clockwork. Imagine a messy, evolving structure where orbits tilt, axes flip, and rotations can be braked, twisted, or even reversed over billions of years. Ask, where are the Venuses in this system? Which worlds are quietly breaking the pattern? Pattern interrupt. Picture a future press conference. We found an Earth-sized exoplanet with a year shorter than its day, spinning backwards under a crushing atmosphere. Instead of thinking, that's too weird, you'll think, of course, gravity, tides, impacts, atmospheres. This is what they do over time. The universe stops being a set of exceptions and becomes a set of clues. And yet, something is above the planets. Something is below them. Once you've internalized Venus's story, that layered reality stops being confusing and starts feeling deeply satisfying. The diagrams are flatter than the truth, but your mental picture doesn't have to be. Now, let's begin turning that upgraded intuition back onto Venus itself and watch how those early collisions, tides and clouds of gas could twist an Earth-sized world into the strangest day in the solar system. So now we can finally circle back to the weirdest headline in this whole picture. One planet in our solar system is literally spinning backwards. Its day is longer than its year, and if you could stand on the surface, the sun would crawl up from the west and sink in the east. That sounded like a glitch at the start. Now it should feel like a question. What story does that rotation tell? Because here's what nobody tells you. That backward spin isn't just a single mystery. It's the sum of every force that's ever pushed on Venus. We began with a common origin, a collapsing cloud of gas and dust, flattening into a rotating disk under gravity. So of course Venus started out spinning in the same general direction as Earth, orbiting in the same broad plane, another ordinary world in a very flat family portrait. Then we layered in the violence. In those first chaotic tens of millions of years, giant impacts weren't rare accidents. They were the way planets finished forming. A Mars-sized body clipping a young Venus could tilt its axis, slow its spin, even leave it wobbling so slowly that later effects had an easy target. You know the one. Uranus, tipped on its side, is our other obvious reminder that these collisions can rewrite what normal looks like. But the story didn't freeze there. For billions of years, the sun kept pulling. Tidal forces reached into Venus's interior and its dense atmosphere, draining rotational energy a tiny bit at a time. Thick clouds and super-rotating winds set up atmospheric tides, so the air and the solid planet were constantly exchanging angular momentum. If that sounds abstract, think of it this way. Every sunrise on Venus is the end result of an ancient tug-of-war between rock, gas, and star. Put all of that together, and the paradox softens. Venus's 243-day retrograde day, longer than its 225-day year, stops looking like a bug in the solar system's code and starts looking like a layered fossil record, a record of a shared birth in a spinning disk, of at least one brutal impact, and of slow, relentless sculpting by tides and atmosphere. From far away, it's just spinning the wrong way. From the inside of its own history, it's exactly what you'd expect. So was the solar system ever a neat, clockwork machine? Or did we just draw it that way because a flat diagram is easier to print? Once you see how completely a planet's spin can be rewritten, the whole thing stops feeling like a static model and starts feeling alive. Directions aren't sacred. Even which way a world turns can be negotiated. And yet something is above the planets. Something is below them. If Venus's day can be turned inside out, What else in this orderly picture is just waiting to be flipped when we change our point of view? So if directions are negotiable, what else is Venus negotiating behind those clouds? Because here's what nobody tells you. For all our simulations and clever theories, Venus is still holding back some of its best secrets. We don't actually know the exact sequence of blows it took. Did one Mars-sized impact flip it almost upside down in a single violent instant? Or was its spin chipped away by a whole chain of smaller collisions that slowly scrambled its rotation? How big were those impactors? What angles did they hit at? And how much of today's backward spin is a fossil scar from that early chaos versus a slow twist from the sun's gravity and that crushing atmosphere? Even right now, we're not sure how tightly the atmosphere and the interior are coupled. The upper clouds race around the planet in just 4 Earth days, while the solid body crawls through a 243-day rotation. Are those super fast winds constantly tugging on the rock below, or mostly sliding past it? Is the molten interior pushing back? Or has the atmosphere essentially taken charge of the planet's day? And the biggest practical question, is Venus's current spin state actually stable? Or are we catching it mid-transition on a time scale of millions of years? So let's start at the very beginning of the next chapter. We're about to get new eyes on this world. Missions like Veritas and Envision will map Venus's surface and gravity field in exquisite detail, looking for buried impact basins, subtle deformations, and hints of recent volcanic activity that can pin down its impact history and interior structure. Da Vinci will dive straight through the atmosphere, tasting its chemistry and pressure layer by layer as it falls, trying to reconstruct what that air was like when the planet was young. Will we find signs that Venus once had oceans? A gentler climate where water could pool and clouds looked more like Earth's than like a pressure cooker? Or will the data tell us it went off the rails almost immediately, its rotation and climate locked into a runaway state from the start? You know the one, the version where Venus isn't a fallen Earth twin, just a neighbor that took a completely different path from the very first spins. Because once we decode one backward spinning world up close, we get a template for thousands of distant orbits. Exoplanets we only see as dips in starlight suddenly become less abstract. A hot, slow rotator hugging its star. A world with a thick cloud deck and a strange day-night pattern. Do we read those light curves and think, that's a Venus story? Or do they force us to invent entirely new chapters? Imagine the moment we first directly measure the rotation of a truly Earth-like exoplanet. Not just its size or its orbit, but how fast it spins, which way it turns, whether its day is being stretched or reversed by some invisible torque. Do we recognize the same kind of atmospheric grip we saw on Venus? The same kind of impact-scarred spin, or something so alien it makes Venus look boring? Now let's begin to see the bigger pattern. The story of Venus's spin isn't just about one wayward planet in our solar system. It's a lesson in how we read the hidden histories of worlds we can never touch. Every weird rotation, every tilted axis, every backwards day is a clue. And yet, something is above the planets. Something is below them. The next time we stare at that flat picture of orbits, we'll have to ask, which of those quiet dots is secretly in the middle of rewriting its entire sense of direction? So now that we've unpacked how a planet can quietly rewrite its entire sense of direction, we have to ask you something. Which Venus are you carrying around in your head right now? Is it the Venus that got sucker punched? In that picture, an early Earth-sized world is spinning the normal way. and then a Mars-sized impactor slams in, off angle, dumping angular momentum, tilting the axis toward upside down, and leaving the planet rotating so slowly that later tides can grab hold. You know the one, the cinematic single-event origin story, where gravity throws one wild punch and the victim never quite recovers. Or are you in the slow twist camp, where no single collision gets to be the hero? Because here's what nobody tells you. If you park an Earth-mass planet that close to the sun, wrap it in a 90-bar atmosphere, and let it orbit for billions of years, the tides in the air can do terrible, patient work. Solar tides tug on the solid body. Atmospheric tides push back from above. And over time, the spin can stall, wander, and finally tip into that retrograde state we see today. Then there's the hybrid story, the messy one. The version where Venus is born spinning prograde, gets smacked a few times in the early chaos, and then has its weird, half-broken rotation slowly sculpted by tides, and that super thick, super rotating cloud deck. Does that feel more honest to you, given how little in the solar system is truly clean and flat and simple? We want to know which camp you find most convincing and why. Drop it in the comments. Are you Team Giant Impact, Team Tidal and Atmospheric Torque, or Team It Takes a Village of Catastrophes? Point to something concrete from the video. Was it the simulations where a Mars-sized body flips an Earth-like Venus? The models where tidal braking naturally steers a slow spinner into retrograde? Or the way Venus's 243-day day and super-rotating winds feel like a fossil record of both violence and long-term sculpting? Here's a thought experiment for you. Imagine we detect an exoplanet. Same orbit as Venus, same thick atmosphere, same close-in bath of stellar light, but its spin is perfectly prograde and reasonably fast. What would that tell us? Would it scream, "No giant impact here"? Would it prove that atmospheric tides can sometimes lose the tug of war? Or would it just widen the picture, showing us that there isn't one Venus story, but a whole plane of possible histories in planetary space? If you're still here, your brain clearly enjoys having its orbits bent a little. Comments, likes, and shares are the gravity that pull long, weird videos like this up through an algorithm that prefers short, flat answers. Now let's begin to zoom out, because once you've met Venus, you're ready for the planet that's not just spinning wrong, but practically lying on its side, and the one that got locked into a resonance so strange it might change how you think about time itself. So now, we can finally zoom all the way out. We started with that comforting classroom diagram of the solar system. Neat rings, tidy arrows, everything marching in the same direction, on a flat plane like a cosmic clock. You know the one. But by following Venus, we've watched that flat picture buckle and twist into something alive, where planets can slow down, flip over, and even spin backwards under the combined pull of impacts, tides, and time. Because here's what nobody tells you. Once you stop treating that diagram as a map and start treating it as a crime scene, rotation becomes evidence. Venus's 243-day backward spin, its nearly upside-down axis, its suffocating atmosphere acting like a giant brake pad in space. Those aren't random quirks, they're clues. They tell you that worlds don't just form and sit there. They get hit, torqued, dragged, and rewritten. So the image we carry forward isn't just Venus spins the wrong way. It's Venus as Earth's twisted twin. Same basic size, same neighborhood in orbit, completely different fate. When you picture it now, don't just see a pale yellow ball. See a world whose backwards rotation is a visible scar from its chaotic past. a permanent reminder that planetary histories are fragile. Change one impact angle, one tidal resonance, one atmospheric tide, and you don't just change the length of a day, you change the entire story of a planet. And here's the philosophical twist hiding underneath all the physics. In space, there is no up, there is no down. There's no absolute right way or wrong way to spin. There's only motion relative to whatever plane we decide to call normal, and the stories we decode from that motion. Call Venus upside down, and you're really just confessing which direction you chose as your reference. Pattern interrupt for your brain. What if we've still been thinking too small? We've talked about impacts, atmospheres, and tides, but what happens when you zoom out to stellar lifetimes and galactic orbits? As the sun brightens and swells, how will that changing gravity field and radiation reshape planetary spins? As our whole solar system plows through the Milky Way's cloud of stars and dark matter, could distant flybys or passing molecular clouds slowly torque the Oort cloud, or even nudge planetary axes over millions or billions of years? What rotational states exist that we haven't even imagined yet? Chaotic, tumbling Earth-sized worlds. Planets locked into bizarre resonances with multiple suns. Or systems where day and year blur into something that doesn't fit our language at all. So, let's start at the very beginning next time you see that flat textbook picture. Ask yourself, what motions is it hiding? What scars is it smoothing over? If you want to keep replacing those old, flat mental models with richer, stranger, more accurate pictures of what actually exists in our solar system and beyond, you know what to do. Subscribe, stick around, and check out the other videos waiting for you on the channel. There's a whole universe of crooked spins and tilted planes still to explore.